Let's look at a couple of examples of using equilibrium in 3D. So this is using our three equilibrium equations. The sum of forces in the x direction equals 0, sum of forces in the y direction equals 0, and sum of forces in the z direction equals 0. That's what we're talking about in our equilibrium here. Those are our main equilibrium equations for now. And we're going to look at this example problem where we have a lamp hanging up and we want to find out if, given the weight of the lamp, which I didn't write in here, but the weight of this lamp is 800 newtons. So given the weight of this lamp here, how much force is each cable carrying? How much force is going through each cable as it's attached to the walls at points D, B, and C? And, this is a problem that we could very well see in real life. If we need to know if one of our cables is overloaded and is going to snap. Maybe we have to rearrange something so that it doesn't snap. Maybe we reconfigure something, and this is just a test problem, right? To see if this configuration works, how much force is going through each one of these cables. So we're going to find the force in each one of these cables using our equilibrium equations, right? We don't want, there's nothing moving, right? Everything is stationary. There's no net force in any direction. Nothing is accelerating. It's all in equilibrium. So we're going to set up our equilibrium equations. So we've got our three equilibrium equations, and before we can set those up, we need to have our free body diagram, which here I'm going to draw my free body diagram at point A, because that point captures all three of my cable forces as well as my weight force. If I draw my free body diagram here, I have the weight of my lamp points straight down in the z direction, and I'm given this one, right? My weight is 800 newtons. And there are several ways that I can write this other than just putting it in my free body diagram. I could make a note over to the side here. I could say, weight is 800 negative, it's in the negative z direction, negative 800 k hat. Or I could even set up a table for myself with each one of these forces, showing their components in each direction, right? So if I make a little table for myself, I can say W in the X, Y, and Z directions, that my W is negative 800 in the Z direction, and then 0 in any other direction. Finish out my free body diagram here. I have my cable AB is located entirely in the Y direction. It does not move up in the Z, up or down in the Z at all, or in the X direction. It is entirely in the Y direction. This is the force in cable AB, entirely in the Y direction. So I would write that in the positive Y direction, I might add. So if I wanted to put that in my table here, force of AB, there is nothing in the X direction. There is nothing in the Z direction. It is entirely in the Y direction. So I'm going to put FAB. There's no ratio needed for anything. There's no sine, cosine, trigonometry, any angles. It is entirely that force in the positive Y direction. What else do I have? I have cable AC, which is entirely in the positive X direction, right? If I draw this cable here, orange, it goes out this way in the positive X direction, FAC. Again, you could call it just FC if you wanted to. You could call it FB, FC, FD. The naming convention, name the forces whatever makes the most sense to you. Something that you can easily keep track of it later. You could even call them force 1, 2, 3 if you wanted to. Just label it so that you know what those forces are when you draw them in your free body diagram. And that when you refer back to them, you can correlate them back to these forces in cable AB, AC, AD. That's what's really important. is you keeping yourself straight in what you're talking about. Anyway, so FAC is entirely in the positive x direction, right? It's pointing in the positive x direction. So if I put it in my table here, FAC entirely in the positive x direction, right? Nothing in the y, nothing in the z. But then it seems so easy, right? It seems so easy so far. Everything is in its own coordinate direction. Everybody's in their own lane. And then we get this pesky FAD. And FAD up here has components in all three directions, right? Which we can tell because it's coming from A. A is in the XY plane up to the Z axis. But notice it gives us these measurements, these distances. And from those, we can actually determine the ratios of each thing, right? So we could go through and create a position vector for AD, and it would be the same process that we'd been using before. But what we can also do here is create the triangles, right? So if I draw in the triangles, I'm going to do this in dark blue. If I draw this triangle here, right, representing the lengths that each goes to. The length of this we could solve for, right? We can solve for what this length of rope here is by doing Pythagorean theorem on this bottom triangle, right? This xy triangle. We can do 2 squared plus 4 squared, take the square root of that. And that would give us this distance here that is in the plane. And we could use that and this 4 to find this distance of AD, how long rope AD is. So 2 squared plus 4 squared is 4 plus 16. Square root of 20 is this length down here. I will do it in yellow. Square root of 20 meters. And then I have this 4 meters in the z direction up. So I can do, again, Pythagorean theorem just to find the length. And I could say, okay, 20 squared, square root of 20 squared is going to be 20, right? That's easy enough. So 20 plus 4 squared, which is 16. 20 plus 16 equals 36. So square root of 36 gives us this distance here of 6 meters. And now I can see that it's already broken up into ratio triangles for me. I have this length here. So I can use these ratio triangles for the X, Y, and Z positioning. Just as we had done in 2D when you were given maybe like a 3, 4, 5 triangle, and you say, okay, well my X is 3 is the X component over the 5, right? So maybe if you were doing f of X, it was 3/5 of f. This is the same concept that we can apply here, where my overall length is that 6 meters. My overall length is that 6 meters, so I would put that on the bottom, right, over 6. And then on the top, for f of x, in my x direction, it is coming out by 2 meters in the x direction. So it would be 2 over 6 times f. 2/6 f is the x component of that cable AD. So I'm kind of just taking a shortcut from doing a position vector, because if we did a position vector, we would find the exact same thing, right? If we found the position vector, the position vector would just be 2, 2, 4, 4, right? Two, 4, 4. And then when we find a unit vector for that, a unit vector of that position vector would be divided by the magnitude of AD, which would be 6, right? So it's the exact same idea. I kind of just took a shortcut here, and I was able to use my ratio triangles instead of going through the whole finding a position vector and then using this unit vector ratio and multiplying it by f, as we had done in some problems before. Okay, so now that I've established how I'm getting these ratios here, this guy out of the way. Get out of here. I don't need you anymore. All right. So now that we've established how we're going to get those ratios, we can put those into our table as well. So our FAB, the x component we just said is this 2 2/6 FAD. Now this 2 here is going in the negative x direction, right? Our coming out from this point on our free body diagram, our coordinate system was given to us, right? Is in the negative x direction. It's going backwards, right? Going backwards. So that position vector I wrote was actually wrong. It's -2, -4, 4. That's my bad. I left off the signs. It's -2, -4, 4. Ugh, icky. Get out of here. So -2, -4, 4, right? Looking at this vector, it's going out from A backwards, right? Back towards the origin point. So it is -2/6 FAD. If we look at our y component of it, our y is going in the negative y direction for 4 meters. So that's going to be -4/6 FAD, right? It's the y component of FAD over the magnitude times FAD. This is essentially a unit vector. This is just a ratio that I've gotten from my triangles, and I'm putting it in this table so I can see all of my x, y, and z components broken up. And then my z component going up from A, my z component here is a +4, right? It's going in the positive z direction, 4/6 FAD. Now, I mean, obviously you can simplify these 2/6 and 4/6, 2/6 is just a third, right? You can simplify it that way. This is just to illustrate where those numbers are coming from, right? That it is the 2 I pulled from this guy here, right? My 2 is my x component, and my 6 is my overall length. But that's all 4 of my forces, right? That's my complete free body diagram that I have for each of the 3 cables, and then the weight of the lamp itself. And I have them all in this really nice little table that I can use to set up my equilibrium equation. So if I let me move all of this, and I just want to do an equilibrium equation. Let's do my z one first, actually, because if I look at my z column, it's the only one with an actual number on it, right? It has that -800. So if I set up my equilibrium equation for z, sum of my forces in the z direction equals 0. Equals, and then I just added everything in this column together. That's all I do. Sum everything down the column. 4/6 FAD minus 800. And since I picked the one that had an actual number in it instead of the ones with variables, I can just solve for FAD, right? So if I add 800 to the other side, I get 4/6 FAD equals 800, right? If I rearrange this. And so I get FAD equals 800 times 6/4. And if I pop that into my calculator, I get 1200. FAD is 1200, 1200 newtons. Alright, so I found one. I found FAD. That's the force in cable AD. It's 1200 newtons. Let me put that... let me just put that over here. Let me put that on my free body diagram so I don't lose it. 1200 newtons. And now that I have that, I can go through and I can solve for FAB and FAC. So FAC, it doesn't really matter what order we do this in now, because both our X and Y column have FAD in them. So I can set up either. I'll go ahead and just go in reverse order, right? I'm going to do the Y component next. So sum of forces in the Y direction equals 0. That's our base equilibrium equation. And then I just sum them up down the column, right? So that's FAB minus 4/6 FAD. Plugging in that 1200 that we just found in here. For FAD, I get FAB equals 1200 times 4/6 gives me 800. 800 newtons is what our FAB is. I'll write that over here. FAB is coincidentally, just like our weight, is 800 newtons. And then I'll do my final equilibrium equation, which is my X equilibrium equation, to solve for FAC, right? That's the only one that we're not sure about, that we don't have yet. Sum of forces in the X direction is 0. So I'll take everything in this column, add it together. FAC minus 2/6 FAD. And again, FAD we found was 1200. So plugging that into my calculator, I get FAC equals 2/6 times 1200 is 400 newtons. 400 newtons. So that would be it. That would be my three answers. My FAB is 800, FAC is 400 newtons, and FAD is 1200 newtons. That's the force in each of my three cables. Which again, might be important to know if, say, your cables are only rated to handle 1000 newtons. You know, maybe you need to change your design. You have to change how this is configured. It's a really good thing to know as engineers, right? We want to know if this system is gonna hold, right? So let's do one more example. All right, here's our final example that I'm gonna work through of equilibrium in 3D. But before we work through it, I'd really like you to pause and try to work this out on your own. At the very least, think about the steps that you might go through when you're setting this up and solving, right? So when we're working through these equations, we have some steps we want to follow, right? We always want to make our free body diagrams and set up our equilibrium equation. In 3D, usually our coordinate system is given to us. So in this example, you can see we have an XYZ coordinate system already set for us. It's oriented a little bit different than we're used to seeing it, but it gives us a really good judge of which things are in which direction so that we can all be on the same page when we approach this problem, instead of every individual using a different coordinate system and getting a slightly different or approach, slightly different answer. This way we can keep things a little more uniform. But please pause the video and try to work this out. See how far you can get, or at least in listing out the steps that you do to solve this problem. I will say you do have 2 free body diagrams required in this problem. And we'll kind of look at each of those, but I'm going to start with just one of them and setting up these equilibrium equations. So we're finding the force in each cable supporting this. which means we're going to be finding the force in cable AB. Whoops, oh, didn't mean to move that, sorry. We're going to be finding the force in cable AB here, cable AC, cable D, cable E, and cable F. So we have 5 cables that we're going to need to solve for each of their forces, which of course means we can't do it in a single free body diagram, right? Our equilibrium equations in 3D give us 3 equations, so we can only solve for 3 unknowns. So that's how we would know that we need multiple free body diagrams in this. Because if we tried to set this all up in one free body diagram, we have 3 equations and 5 unknowns. It would be literally impossible to solve for. So we can use multiple free body diagrams at multiple points to find our missing information. I don't like those lines there. Let me get rid of those. I'm going to go ahead and I'm going to start my first free body diagram at point A. And the reason that I want to start it there is because A, I know the weight of that crate, right? This crate hanging off of point A here, I know the weight of it. It tells me in this problem statement that it's a 500-pound crate. So I know that I'll already have a known force that I'll be working with. And then 2 is that I can see that this is actually entirely within one plane. I'm sorry if you hear like scrunching noises in the background. My dog is chewing on something. Just, that's what that is. I'm sorry if you can hear it. But I can see that this is entirely within one plane, right? These lines in the background indicate, let me draw them, let me highlight them in red here. These lines here are indicating to me that these are all existing within the same plane. They're all in the XZ plane. They're offset from the XZ plane, but they're all within the same plane. So when I draw this free body diagram, I'm going to do this one in blue. I have the weight coming off of it, weight of the crate, which we knew was 500 pounds. And then I have cable AB, which I'm just going to label as FB in this case. FB, again, it's entirely within one plane, meaning this is actually just a 2D system at point A, right? This free body diagram at point A. Where I have this is a 20-degree angle. And then I have cable AC, which is coming off at a 35-degree angle. I'm going to call this FC. For the force of cable AC, this is a 35-degree angle. And this, sorry, I misspoke. This is not offset from the FZ plane. This is in the FZ plane, and we can tell because we have these lines all telling you, all aligning you to the XZ plane here. That's what these smaller, thinner lines are doing in this problem for us. So let me... Oh, so we have our free body diagram, right? This is our entire free body diagram, and in this case, it's a 2D free body diagram, right? Everything is in the XZ plane, so it's only X and Z components here. So if I wrote out my equilibrium equations for this, I am only writing out the sum of forces in the X direction is 0, and the sum of forces in the Z direction is 0, because my coordinate system here is X, Z. That's the plane that this is operating in here, right? X and Z. So I can set up these equilibrium equations just as we had done earlier in 2D systems, right? So my Fx system is going to be the X component of FB, which is going to be FB cosine, because it's adjacent, FB cosine 20, and it's in the positive X direction. And then my FC also has an X component in the negative X direction, which is minus FC cosine 35. Right, so that's my equilibrium equation for fx. I can also set my fz equation up, so this is going to be the y component. Let me do this in a different color just to make it a little clearer. So my fz, do this in blue. Fz is going to be the z component here of fb, which is going to be sine 20, right? Normally we might have called this fy if we were working in the fy coordinate, or in the xy coordinate system, but this one's xz. So this is going to be fb sine 20 plus, right, our fc is also operating in the positive z direction, plus fc sine 35 minus, this w is entirely in the negative z direction, minus 500, right? And this is an equilibrium, so we set it equal to 0. So now I have two equations, two unknowns. I can already go ahead and solve for these two cables without having to set up anything else just yet. I know that I can find just these two cables from this free body diagram. So I'm going to go ahead and use my z equation here. No, I'm actually going to go ahead and use my x equation, and I'm going to set up a relationship between fb and fc. So I'm going to go ahead and say fb equals, maybe it would make more sense if I did this in yellow, just to be consistent here. All right, fb equals, if I add fc cosine 35 to the other side, then I divide everything by cosine 20, equals fc times cosine 35 over cosine 20. So now I have this relationship of fb to fc. I can plug this in to my z equation, right? Just the basic algebra that we've been doing, system of equations. And I can plug that in and I can say, all right, my fc times cosine 35 over cosine 20 times sine 20 plus fc sine 35 equals 500. So all I did was substitute in that fc and then moved this 500 over to the 0 side here, right? Added 500 to each side. And this gives me, if I combine these two terms in my calculator here, I get 500 equals 0.87 fc. And solving for fc, you know what, I'm going to put him under my diagram here because he's one of my answers, right? fc equals 574 pounds. I've got my 574. I plug that into this equation, again, fc, so 574 times cosine 35 over cosine 20. Plug all of that into my calculator to find what fb is. And I get fb is 500. Just coincidentally. FB is 500 pounds. Right, so that 500-pound force is creating tension in those cables equal to the tension in cable C, or AC, or however you want to label it. The tension in that cable from A to C is 574 pounds, while that tension in cable from A to B is 500 pounds. That's how much force each of those is feeling. So I've got two of my cables, right? But I still have those other D, E, and F points. So I'm going to go ahead and create another free body diagram, this time around point C, to go ahead and see if I can solve for those cables. Let me get rid of this. And let's just start fresh here with a new free body diagram, this time at point C. And I'm going to do him in green here. So at point C, if I do my free body diagram around point C, I have cables E and F here, right? So I'm going to call this FE. This one is FF. I have DFD coming off this way. And then I have that FC that we had just found, right? So I have 3 unknowns, and then I'm going to have my 3 equilibrium equations, because this free body diagram is set up in 3D. So I'm going to go ahead and set up each of these, just writing out my table to see what all of these components are, because with the 3D free body diagrams, it can be a little bit difficult to see which direction things are pointing in, and sometimes it's easier to kind of refer to both your free body diagram and the original prompt that you were given to break everything down into its components first and then set up your equilibrium equations. So like in the last problem, in the first example we did in this video, we set up that table. I'm going to go ahead and set up a table again to kind of keep everything straight in my mind. So I'm going to go ahead and do FC. I've already got in blue here, right? FC is 574 pounds, which means that I can actually find the value of each of the components of FC, right? So we said FC is entirely in the X and Z directions, right? My FC triangle is set up like this, where this is the FCX component and this is the FCZ component with no Y components in it, right? So if I put this in my table and I said FC X, Y, Z components, my X component I would say is FC. My X component is FC times cosine 35. And I'm going to go ahead and plug in this 574 in for FC so that I can find the actual value here. And I don't... Do I have it written somewhere? I don't. Okay. Let me punch that into my calculator real quick. I've got 574 times cosine 35, and I need to make sure that I am in degrees. Oops, 574. I was not. I was in radians. 574 times cosine 35 gives me 470. All right, so I'm going to go ahead and just put in 470. I'm not even going to bother with keeping it in as the variable because it's a known value, and it's going to be easier for me just to keep it straight as a known value at this point in the problem. What did we say? We said this was 470, and it is going, if we look at this here, it is going in the, might help to put my XYZ on here. This is my positive Z direction. This is my positive X direction. And then my positive Y direction is actually going back out this way. So that's good to note. It's going kind of back into the page. Away from us is our positive Y direction, according to this diagram. Alright, so my FC is in the positive X direction. It was 470, so it's a positive 470. My Y, we said there was no Y component in this, right? It's entirely in the XZ plane, as we established in the beginning part of the problem. And then we have the z component, which the z component of this is going to be FC sine 35. So I'm going to hit 574 times sine 35 gives me 329. 329 newtons. So that's my FC, and I can break up all of these others in exactly the same way, right? So I can say, let me move this and use this as a workspace up here. You get out of here. What should we look at next? Let's go ahead and look at FD. FD here, we can see, that wasn't right. Whoops. FD is in the XZ plane, just as the other FC was, right? And we can tell by those thin lines. It's telling us that it exists in the XZ plane. That is this line right here, and these lines tell us it is in the XZ plane, where this is 10 feet and then this is 24 feet. If we draw that triangle, we can use this ratio triangle, right? 10, 24, and then I can solve using Pythagorean theorem for what that distance is to get my ratio triangle. So square root of 24 squared plus 10 squared gives me 26. 26. Another very even special triangle. Not one we come across a lot, though. So 10, 24, 26, which means that this, remember, this is my x component and this is my z component. There is no y component here for FD. So I have FD in the x direction is going to be FD times that ratio. In the x direction, it's 10 over the total 26. So my FD 1026, and notice it is going in the negative x direction, right? The negative x direction. So this is a negative 1026 times FD. Negative 1026 FD. And do the same process for my z component, right? FD in the z direction is a positive. It's going in the positive z direction. With the component of 24 is the z component times FD, right? 24 26 FD. That leaves me with these last two forces, E and F. And there's something really interesting that we notice about E and F here, which is that they're exactly symmetrical about the y-axis. So when I set up these triangles, let me move that guy. When we set up these triangles, we notice they're the only ones with y components, and they're exactly symmetrical. So when we work through it, what we're going to find is that their y components are exactly the same, right? If I set up, this is entirely in the zy plane, right? Looking at E here, it has these thin lines telling me it's in the zy plane. I'm gonna do it this way instead. Okay. Right, so here's my FE. This is 7 feet along the bottom, and it is 24 feet up. So I can plug that into my Pythagorean theorem. I can go 24 squared plus 7 squared take the square root of that, and it's 25. So I have another special ratio relationship triangle, 7, 24, 25, to set up the ratios for FE as well as FF, right? Because they're exactly symmetrical. They have the same dimensions. Just one goes in the positive y direction and one goes in the negative y direction. So when I'm setting these up, I'm setting them up exactly the same, right? So FE is going to be no x component, right? Entirely in the zy plane. And we can say the same for FF. No x component, entirely in the zy plane, right? Because in this case, this is our, the 24 here is our z component, and this is our y component, right? So all we've done is we're just reorienting the triangle so that we can see it face on. So we look at our y component here. For E, for FE, it's going back. It's going into the page, which we know is the positive y direction because that's what the problem indicated to us. It indicated this is the positive y direction. So FE is going to be that ratio relationship 7 over 25 times FE. That's the y component of FE. Is 7/25 FE. Now the z component, it's going in the negative z direction, right? Negative z direction. And it's going to be 24/25 of FE. Negative 24/25 FE. And again, FF is set up exactly the same way. It has the same negative z component, exactly the same triangle setup. The only difference is the y component is in the negative y direction, right? So instead of being in the positive y direction, it's in the negative y direction. But it's exactly the same. Negative 7/25 times FF. And then the z component is exactly the same. No sign change or anything. Negative 24/25 FF. So with this, I can set up all of my equilibrium equations, right? And I'm going to start with, honestly, you could start with any of them. The x or the y we could see are going to be the easiest ones to set up. Because if we just look at the y's, for example, we can see we have 7/25 FE minus 7/25 FF equals 0. Well, what does that mean, right? We move the 7/25 over, we get 7/25 FE equals 7/25 FF. Divide that out, FE equals FF, right? Which we discussed we could see by symmetry in the problem. We could see by symmetry that it was going to work out that FE was going to equal FF, at least in the y components. But now we've actually proven that FE equals FF. So FE equals FF. I'm going to look at the x components just because my z components is busy. There's a lot going on in here. I've got 3 different variables in there. I don't know those variables. I'm going to come back to that, right? I want to start with the simplest ones first. So for me, that FE equals FF, about as simple as it gets. And then I see, okay, well, I've got, 470 minus 10/26 FD equals 0. That means I can solve for FD, right? I'm going to go ahead and set that one up. Move all this junk out of the way. If I set up this x equation here, equilibrium equation, sum of forces in the x direction equals 0. equals, and then we're just adding them down the column, right? 470 minus 10/26 FD. If I add that over, I get FD equals 470 times 26 over 10. And when I plug that into my calculator, I get FD is about 1,222 pounds. Somewhere around there. I'm going to put this down here so I can keep track of it. FD equals 1,222 pounds. So now I've got FD, which I can plug into my chart if I so desire, right? I can say now, plug into my calculator, 1,222 times 24 over 26 gives me this value is now, go ahead and put this in this orange here. This value is now 1,126. Just plugging in 24 over 26 times 1,222. I have an actual value here now. And then we know FE equals FF, so we can just say that these are exactly the same. I'm just gonna call them F now. Right? I'm just gonna call them F when I set up this problem. So I'll set up my final equilibrium equation, which is adding everything in the z direction. So my equilibrium equation about z, sum of forces in the z direction, 0, equals 329 plus 1126 minus 24/25 times F minus 24/25 times F, right? Just adding everything down the column here. Add those all together, and I get F, right? Just rearranging the equation, and I can solve for F. F is going to be about 416 pounds. Right, and of course this F is the same as this FE and FF. I just relabeled it. So in my final answer, my FE equals 416 pounds, and FF equals 416 pounds, right? Because we said those were the same. So that's all 5 of the cables that we had discussed, right? Cable from A to B, cable from A to C, cable from C to D, cable from C to E, cable from C to F. Those 5 cables now all have forces. And you could write it like this. You could leave them as these force listings here. You could also go ahead and say, AB, AC equals all of these things. But when they're asking you to determine the force like this, they're just asking for the magnitude, right? You don't need to give a direction because everything is already in directional form. We're not looking for a Cartesian form. We're looking for the very practical, how much force is going through this cable, the magnitude. This is the actual practical form that we would see in real life. And that's it. That's the whole problem. It can get a little long doing these, right? When you have to do these multiple free body diagrams, you're solving for so many unknowns by just going through this process over and over again. But it's the same steps over and over again. So even within one problem, you can get a lot of practice of just doing the steps and doing them correctly.